Okay, so I will. Okay, I think I'll just start from here. So Fourier transforms are useful for describing multi-scale systems. So we have a signal which is pretty complex signal, and so we can write them, describe the signal as a sum of sine or cosine waves. Image processing, of course, as I said, is useful. Structures at different scales in a hurricane or in a tornado. Interaction across scales, Fourier transform is very useful, and accurate derivatives. I'll come to it in a while. So let's start with definition. 1D Fourier transform, but I want to be specific, is C to C. So my data is complex. Okay, so this data is complex. C for complex and R for real. Okay, so many examples, like the Schrodinger equation, psi is complex. So in real space, my function f is a complex field. Okay, so and that complex for that field we define a Fourier series. Okay. So the definition of Fourier series is from the real space. Whether I'm in real space, X is called real space, like Schrodinger wave function of electron. So it is in real space, psi of x. Now, but we denote in this set of lectures, my function is f. Okay, so f. So any f of x. So this is a theorem by Fourier. So any periodic function. So this function was a periodic. Periodic means I take any point x, then x plus l. So my function f of x equal to fx plus l. Okay, so period is l. Okay, so we don't need to save all the data. We save only from 0 to l. But remember that this data here is same as this data here, right? Because f0 equal to fl. Now this periodic function, and there are some more qualifiers. Okay, it should be continuous, differentiable, except at some isolated points. So the piecewise discontinuity is allowed. Piecewise continuous. Okay, but we'll ignore that. We'll assume in this set of lectures that a function is smooth. Now this periodic function can be expanded as a series of Fourier basis. Okay, so this is Fourier basis e to the ikx. Now I have many kns. So k is there, many of these, and and kn is defined as 2n pi by l. Okay, n is an integer which goes from minus infinity to plus infinity, and so this is a wave number. No, it's called wave number. Wave number. So we write as a e to the power I knx. Okay. Now there is a amplitude in front. It's like amplitude of the wave. Okay. So f at n. So we have got f at n. So and we just sum it up. Okay. So here shown here, like we have wave number 0, 1, 2, 3, da 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 to infinity, and in the left side we have -1, -2, da da da. Okay. For every wave number there is a amplitude. Okay. So as I said, we have a lot of this Fourier thing, and each of them has amplitude, and that is written as f at n. So straightforward. Now we can invert this just straightforward using the orthogonal property of Fourier series. You may know that e to the power minus I knx dx 0 to l is l if kn is 0. So delta kn 0. Okay. So it's a chronicle delta function. So using this property, you can show this. I will not show it, but you can do it yourself. Okay, so just straightforward. So this one, this is given f at n, I get fx. So this is called inverse transform. Inverse Fourier transform. And given fx, I compute f at n, is called forward transform. Okay, so from real space to Fourier space is forward, and from Fourier to real is inverse. Now this is the standard definition. In mathematical physics, you might have seen this is a Fourier series. This is called Fourier series. And Fourier transform is when L is infinity. So when the box size is infinity. But in computational physics, finite box is also called Fourier transform. Okay, infinite box is also called Fourier transform, but this is referred as Fourier transform. Okay, so this is a community notation. Now we go to discrete Fourier transform. Why? Because in computers, this integral which I had in the previous slide, the integral, this integral cannot be done in computers. No, computer has to have finite, basically a sum, quadrature. So when I do the quadrature, then I get discrete Fourier transform, and the dx will not be continue. X is not continuous. X is discretized. X will be discretized. So discrete Fourier transform is what we do in computation. So this is fine. This is discrete, right? This is discrete sum which computer can do, but this one computer cannot do. So we make a discretization of x. This so 0 to n minus 1. Well, let's put it. I mean, I'm going to make it very specific. Please pay attention to this. So this is 0, x equal to 0, and this is x equal to L. But since 0 and L have the same value of the function, so we do not save this one. We do not save this. So we save only up to n minus 1. 0 to n minus 1. Okay. And there are endpoints. So there are endpoints. And the dx is L by n. Okay. So I'm going to substitute it here. So f at n. So dx will be L by n. And the 1 by L sitting here. So integral will be fj. So xj is j times dx, delta x. Okay. So fj times e to power minus I kn. Now kn is, remember I said 2 n pi by L. Now xj, I have to substitute x as xj, which is j times dx is L by n. This cancels. So, and this L will cancel with this. So 1 by n, and there's sum as well. No? This sum fj, j, exponential minus 2 pi by n, I, this I is square root minus 1, and n j. Okay. So this is what we get as a argument for the exponential. And there are many of them, and for what is varying for this, for a given, so for computing f at n is fixed. So j is varied. So j is varied because I'm summing over j. Now here also you need to substitute for I e to I k n x this expression. Okay. So this is how we compute in computers. So this I have rewritten it. Okay. So we have for C to C, we have n of these, and we'll have n of these. Okay. and you can write this as a matrix. So f at 0 f at of n minus 1 equal to this matrix, which will be combination of exponential, and the right hand side will be f0 f1 fn minus 1. Okay, so we get all this. It's a matrix equation, and the determinant of the matrix is not 0, so it's invertible. So given f's in real space, we can get f hat and vice versa. Okay, so so there's one-to-one mapping from f to f hat and vice versa. And how much time will it take for this operation? To compute one f hat n, I had to do how many multiplication and how many additions. So remember, so the j goes from 0 to n minus 1. So there are n multiplication, no? So n of this multiplication. And then I have to sum them up. So n mult plus n sum. Okay, for each of them. So, but there are n of such things. So it is 2n squared. Real operation. So n squared multiplication and n squared summation. So time complexity, if I just do it naively by this way, is order n squared. Okay, order n squared for large n is expensive. Remember this 1D, but in 3 dimensions, the number of points could be, let's say, 1000 cube. So the billion, right? 1000 cube has billion points, and we can show that in 3D is basically n squared again. So it's going to be 10 power 18, and 10 power 18 is not possible even with the best computers. So it's possible, but it just takes too long. Okay, that slide is coming a bit later. So this is called fast Fourier transform. I'm going to show you a bit later. Okay, so there is a trick to do it fast. So these Fourier transforms, f hat, satisfy certain properties. So one property is f hat n is same as f hat n plus n. How do I show it? Just straightforward. F hat of n plus n. So everything remains the same except the exponential. Inside exponential, what do I get? I minus 2 pi j. So instead of n, for n, I substitute n plus n divided by n. So the new thing is this n. So look at it carefully. It is minus 2 pi by n j n n. So this cancels. So what is exponential I times minus 2 pi j? It is 1, right? J is integer, so it is 1. E to the power 2 pi j, it is 1. So that is why this term is 1. So the remaining part is exactly the same as what we got for f at n. So this is f at n. So this is how we prove that f hat of n plus capital N is equal to f at n. Okay. So with this property, we can do something interesting. So in real space, data is saved from 0 to n minus 1. Remember, this last point is not saved. So this, because it's periodic, we don't save the end point, because this is the same as that in real space. Okay. So for capital N equal to 8, I have saved 0 to 7. In computer notation, if you may recall, my wave numbers go from minus n by 2 to plus 1 to n by 2. This was there in the sum. I didn't emphasize it, but there are 8 of them, right? Because it's a one-to-one map. So 8 of them are 0 to 4 for n minus 1, minus 2, minus 3. So these are 8 of these. Okay. So this physics or math notation. So there are negative wave numbers and positive wave numbers. However, using this property f at n equal to f at n plus n, we can shift this minus 3, minus 2, minus 1 to positive values. Right? How? So minus 3 plus 8, right? Because this capital N is 8. So that is 5. So f hat minus 3 is same as f hat of 5. So I just can save it, I can put it here without any problem. Similarly, f hat of minus 2 is same as f hat of 6, and minus 1 is 7. Okay, so in computers we save from 0 to 7, and it's nice. Our indices are positive. Okay, so it's easy to handle. I mean, Python we don't want to have negative index, so that is a problem. So this is very useful transformation. Okay, so this always, so in your Python output, your numbers will be f hat will be 0 to n minus 1. It won't be minus n by 2 plus 1 to n. Okay, and if you want some negative wave number, then you have to do this transformation and get values for negative n. Okay, now here is a trick how to do the Fourier transform in a fast way. Okay, so that's why the word fast is here, fast Fourier transform. And this was by these two engineers, Kelly and Tukey. So imagine that I have 8 data points. So 0 to 7. I'm only giving you the idea. I mean, the whole derivation is quite long. So what Kelly and Tukey do is they divide the data into even and odd indices. So even will be these, you keep on one side, and odds are these. Okay, so the whole data f at n, you write the sum. Even part is in fact fj e to the power I da 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 2 pi so on, and plus odd fj, even, odd. It turns out a factor will come out of this, and this can also be written as 0 to 4, 0 to 3, and this is 0 to 3. Okay, so that's the trick. You can write this big data with 8 points into 2 smaller series whose are written as 0 to n by 2, n by 2 minus 1 in fact. Okay, so we have taken a bigger problem and reduced it to a smaller problem. Now this has n by 2 data points. It can again further be divided to even and odd. Okay, and these two can be divided even and odd, and we can keep going down like that. Okay, so this is similar to binary search. So we did binary search. We made a tree. So less than midpoint and greater than midpoint, and da da da. We keep doing like that. So binary, normally once you divide in binary, you get a log n factor. Okay, so overall, with the n data points, so this is kind of divided in half like that. So overall order for FFT, fast Fourier transform is called FFT, is order n log n. Okay, so this is the order of this algorithm, and this strategy is called divide and conquer. Okay, so we divide the data into half and conquer. Okay, so it is very common strategy in computer science, and this is what is adopted in FFT. Okay, so the Python FFT, Python Fourier transform is FFT. Okay, in fact, it's written in C, so it is quite fast.